Guys. So today I'm going to talk about specific heat capacity and temperature changes within a phase of matter and the energy calculations associated with that. Here I am in the storage closet because this is where I found space and it's quiet. So let's get on with it. So as a quick recap, the other day we talked about energy associated with phase changes. And that is when our temperature is constant. So we talked about changes in potential energy of substances, when we're changing the phase to liquid to gas or solid to liquid. So, but what happens when we're changing temperature? These here, the temperatures are constant. And we use the Q equals M times delta H, where mass is M and enthalpy depends on the phase change it is. So let's talk about that right now. So there are three factors that affect how much energy it takes to absorb or is released. And those are the substance itself, how much the temperature is changing, and the amount of substance. Think about when you're heating up something in a pot of water. So, for instance, the substance it takes, the water is going to heat up differently than the metal. The substance matters. How much you're increasing the temperature. If you want a bigger temperature increase, it takes more energy. And lastly, the amount of substance. If I have to heat up more water, it's going to take more energy to do that. So write this down, guys. Specific heat capacity is the ratio of energy to the mass and temperature change for a substance. Okay, so that's a big idea. Oftentimes, we use the shortened version, just call it specific heat. The specific heat capacity of liquid water is 4.184 joules per gram degree Celsius, meaning that in order to raise the temperature of 1 gram of water by 1 degree Celsius, one would require 4.184 joules of energy. And we're going to use this to calculate energy changes within a single phase of matter when we're changing the temperature. So we're talking about temperature. We're referring to changes in kinetic energy. So we're not going to talk about what if we have a temperature change and a phase change yet. We're going to do that in future classes. But this is part of it. So if I want to take 1 gram of water and increase it by 1 degree Celsius, it requires 4.184 joules. How much energy would it take to increase 2 grams of water by 1 degree Celsius? Well, let's use this constant here, the specific heat capacity of water. And let's kind of look at it in this format. 4.184 joules is the amount of energy for every 1 gram of water to go up 1 degree Celsius. So I have 2 grams of water going up 1 degree Celsius. It's a little over 8.3 joules. Okay, so it's double the amount it takes 1 gram of water to go up 1 degree Celsius. What if I want to increase 1 gram of water by 2 degrees Celsius? Well, I'm doing 1 gram of water by 1 degree Celsius twice. So similarly, for 1 gram of water to go up 2 degrees Celsius, it's also going to take that same amount of energy, 8.368 joules. What if I want to take 2 grams of water and increase it 2 degrees Celsius? I do something similar, and hopefully you guys are seeing what I'm getting to here. 2 grams of water to go up 2 degrees Celsius, it's going to take about 16.7 joules of energy. Let's take it to the next step. What if I want to take m grams of water and increase it by delta T degrees Celsius? How much energy would that take? Well, let's put in my variables here. Q being the amount of energy, M, mass, C, specific heat capacity, and delta T, meaning change in temperature. We can only use this, however, when we're in the liquid water phase changing temperature there. So that's a key thing to pay attention to. So write this equation down. Q equals M times C times delta T. You're talking about it whenever you have a temperature change within a phase, changes in kinetic energy. Mind you, the specific heat of liquid water, gaseous water, and solid water are going to be different. So you'll receive all those constants all the time. So not something you'll have to memorize. Here are our variables defined. Q, amount of energy. M, mass. C, specific heat capacity, oftentimes referred to as just specific heat. Delta T, triangle T, means temperature change. So let's take a look at my variables in units. It is very important to pay attention to variables and units. It helps us communicate. So, and they are different. The variables are things like that we use in an equation to represent numbers. The units are used to describe the property. The one big thing that a lot of people struggle with is, well, and you have to pay attention to it. The variable we use for specific heat capacity, C, and degrees Celsius, the unit of temperature change. They both use the same letter, but they mean very different things. One is a variable and the other is a unit. So be aware of that. So why don't you guys pause now for a second and see if you can calculate how much energy is needed to increase 25 grams of water, liquid, from 10 degrees Celsius to 14 degrees Celsius, given the specific heat of water is 4.184 joules per gram degree Celsius. So why don't you guys pause this now, and you guys can try it out. Otherwise, I'm going to go over it now. So I want to solve for the variable Q. And Q is the product of mass, specific heat, and temperature change. So let's identify my variables here. The units will help you do that. So the M, the mass, is 25 grams. The specific heat capacity of liquid water is 4.184 joules per gram degree Celsius. The temperature change of the water I'm referring to here, 10 degrees Celsius to 14 degrees Celsius, the temperature change is going to be 4.0 degrees Celsius. Don't harp too much on positive and negative values for temperature change and energy. That's something we'll talk about later. We're going to talk about it mostly in terms of absolute terms. So let's move on. To calculate Q equals MC delta T, I just take the product of all those numbers. 25 grams times 4.184 joules per gram degree Celsius times 4 degrees Celsius, I get a value of 418.4 joules. Now, mind you, that my units do cancel out as well. Grams here cancel out grams in specific heat. Degrees Celsius here cancels out degrees Celsius in the specific heat. So the unit I'm left with is joules. Now, if you're canceling out units and you have a weird unit that doesn't cancel out, that might mean you used your equation wrong or put a variable in the wrong spot. So here's another style question where we're calculating something different. We're calculating a temperature change. And why don't you guys pause right here and see if you guys can solve this problem. Otherwise, I'm just going to dive right into it. If one adds 1,800 joules of energy to 30 grams of aluminum, where the specific heat of aluminum is 0.90 joules per gram degree Celsius, what is the temperature change? So in this case, I'm going to be using the same equation, yet I'm going to be calculating something different. Temperature change and energy are different properties, so we can't interchange them. So let's identify what we have using some algebra in order to calculate the temperature change. I divide both sides by MC, and I have delta T equals Q over MC. So I just have to substitute in my variables there. My heat or energy is 1,800.0 joules. My mass is 30.0 grams. My specific heat capacity is 0.90 joules per gram degree Celsius. And that ends up being equal to 1800 divided by 27. Remember, I would need to calculate the product of the mass and specific heat capacity first. So if you're using a calculator, make sure you pay attention to order of operations and you don't end up multiplying it. So that's why I have the parentheses there. So I get a value of temperature change is 66.7 degrees Celsius. If the aluminum started at 20 degrees Celsius, what is the final temperature? Well, I'm starting at 20 and my change is 66.7. I'm adding energy. You do need to pay attention to the context of what you're trying to solve. And I just simply add my final temperature. I get from adding my initial temperature to my temperature change. And we know it's adding because I'm adding energy to it. So I get 86.7. So we're going to do some examples of these in class. So I hope this helps, guys. And I'll see you guys later.